Okay, hopefully you can hear me.
Yeah,
Great.
loud and clear.
So yeah, thanks for the introduction and for having me. As Julian mentioned, I'll be kind of changing topics a little bit from climate modeling to focus more on solely the machine learning aspect. As we just heard, for example, machine learning can complement climate modeling in many different tasks in many different ways. So in this talk, what I'm going to focus on is uncertainty estimations using neural networks, which is one specific type of machine learning methodology. Yeah, I'm going to go over some ways that we can create and evaluate our uncertainty estimates from neural networks. So first, I will acknowledge the team that I worked with. As Julian mentioned, I will primarily in this talk be going over that paper that we just recently published, and these are the people that helped us to do this sort of work to kind of give this overview and look at some uncertainty estimates with neural networks. And I've also given the link to the paper here, as well as a lot of the code that I'm going to be discussing is available on GitHub, and it is at that site that's shown there at the bottom of that slide. So to get started, I'll just give you a brief outline of what I'm going to go over today in the talk. I'll start with a motivation and then move on to the uncertainty components just to make sure that we're all clear with what we're trying to estimate when we talk about uncertainty estimates. And then I will go over some simple methods to estimate uncertainties using neural networks, and then some simple methods that we can use to evaluate the uncertainty estimates to see if they're any good. And then I'll just conclude with some ending remarks. So just before I get into the rest of the talk, I will kind of say that the intended audience for this talk is kind of more for novices or people who might use neural networks, but they don't really know about how to get uncertainty estimates from the neural networks themselves, or more intermediate people who have tried some uncertainty modeling, but they want to learn more about other methods and evaluation. But if you're an expert at, machine learning models and uncertainty estimates, this might be your time to sort of sit back and enjoy your coffee or tea. So I'll start with the motivation for this work. So neural networks, as we have seen, are widely used in weather and climate applications. As I mentioned, there really are many tasks that can be very complementary to all sorts of different climate modeling projects and things in oceanic and atmospheric tasks. However, classical neural networks themselves have no awareness of their limitations. They simply deliver a result or prediction. They may deliver some sort of confidence score, such as for classification tasks, they could have, say, a softmax layer that provides a pseudo probability, but these are not really reliable. They're not really meant to provide an uncertainty estimate that the model is predicting along with its, central prediction. However, in the scientific world, we know that we really do want a reliable uncertainty estimate itself. And this can come in many different forms. We can have a probability distribution, such as the parameters of a normal or Gaussian distribution, as we just heard in the previous talk. Or we can have like non-parametric summary statistics, maybe a confidence interval or a histogram or quantiles. Or also we can have just different ensemble members that then that range of the ensemble members themselves might provide some estimate of uncertainty. So for the rest of this talk, I will be using a real-world application to demonstrate the concepts that I'll be going over. And the application that I'll be using is to use machine learning to improve vertical profiles of moisture. So what we have shown here are two different profiles of moisture throughout the atmosphere. So in the black are our observed dew point profiles, or that's what the TD stands for, is that dew point temperature throughout the atmospheric column. And then the blue line represents the profile that is predicted by the machine learning model. And then at each individual level, what we can see is the 95% uncertainty estimate that's being produced by the model. And so what I want to highlight is if we look at the profile on the left, what we see is about 700 millibar level. We see that the model and the machine learning estimate are very close in alignment, and our uncertainty estimates are much tighter around at this level. If we look, however, at the profile on the right, at that same, just above 700 millibar level, what we see is that the model and the observations are quite different. And fortunately, our uncertainty estimates there are much wider. So we can see that in this case, the uncertainty estimates that the model is producing could be very helpful to people that are using this model to give them an idea that they might not trust the profile on the right as much as they would the profile on the left. So now we need to go into a brief discussion of the uncertainty components that we're trying to estimate and go over some of that vocabulary of the components that we're trying to estimate. So in the machine learning community, they distinguish two uncertainty components, and these are the aleatory uncertainty and the epistemic uncertainty. But before I go more into depth, I will give a word of caution that the papers make these concepts of aleatory and epistemic uncertainty sound, that they're very unambiguous and straightforward. However, they are quite complicated, or at least we found that to be the case. They're very slippery concepts, and they really are dependent on different communities and different contexts. So in fact, another paper that we've read is by Bevan in 2022, illustrated 4 different definitions in the terms of aleatory and epistemic uncertainty that are used in different communities. So I just want to shout out a caution that you need to be careful when you're using uncertainty and when you're using these component definitions to know which definition you're actually using, as many papers don't necessarily make this clear. So now I'll delve into the definitions that we see most often in the machine learning community and the ones that I'm going to use throughout this paper. So for machine learning aleatory uncertainty, this is really sources of uncertainty that are inherent in the data. So this includes uncertainties that have to do with internal variability of physical processes, such as just the chaotic nature of processes, or any uncertainty that has to do with data and observation error, such as observation error if the data is observed, or physical model error if data is from a physical model. In contrast, the machine learning epistemic uncertainty has to do more with anything else. So basically, this comes with anything aspect of the machine learning model itself. So sources of uncertainty from this might be structural error, such as if we have incorrect machine learning model structure, or if parametric error, if we have incorrect model parameters, or out of regime error. And this is errors that might occur if we're asking the model to predict and make these predictions outside of what we have trained it on. So just to kind of highlight how different communities do see these divisions differently, as I just discussed, the machine learning definitions kind of divide the data uncertainty components as to whether or not the uncertainty is in the data. So if it's in the data, it'll be aleatory uncertainty, and then everything else is dumped into this epistemic uncertainty. However, in math, the dividing line is whether the source of uncertainty is stochastic or not. So that actually means that some of that uncertainty that would have gotten dumped into the aleatory in the machine learning definition is now going to be shifted to epistemic in the math definition. So just again, highlighting that these dividing lines are very different, and it can get kind of confusing as you're reading papers. So make sure that you kind of know what definition that you're going along with. And that's important just so that we can really understand as we're reading and we really know what we're talking about. And I will just also give a shout out to these other papers that we've also read and that are also cited discussing these concepts, and they really do a great job of going over this aleatory versus epistemic divide in more depth. But I will conclude this section just by giving the classic aleatory versus epistemic example. So what's shown here is just a simple example of kind of their classic aleatory uncertainty on the left and epistemic uncertainty on the right. So the blue dots then are training samples, and then the red line is what we're going to get from our machine learning model. And on the left, we see that aleatory uncertainty. So here, for a given x, there's no unique value for y, and that's because there's just internal variability of the system. The model, even if it's perfect, just can't get it exactly right because of the stochastic nature that's seen in the data. So that's our classic example of aleatory uncertainty. Then if we look on the right, that's epistemic uncertainty, and that's kind of getting at that out of regime error. So in this case, we're asking the model to make predictions, but we don't have enough training samples for the model to fully learn the relationship that the data is trying to tell us. So that could possibly lead to large errors. So those are our classic examples, and I'll just say that in this example, the machine learning and the math definitions align. But that's because it's idealized, right? Because we're looking at only the internal variability, and as we saw, the math definition is based on that stochastic dividing line, so they align here in this case. However, I will, again, just one last time, just kind of hammer in the concept that it does depend on community and context. So for the machine learning community, that dividing line is slightly different. And in that case, that also makes it context dependent. So for example, in the machine learning community, if I actually add more predictors and I don't increase the sample size, that actually could shift some of that uncertainty between these two components. So I could actually end up decreasing some of the aleatory uncertainty because I'm increasing the information about the system. But at the same time, I'm increasing the epistemic uncertainty because I might actually need more data to be able to actually make those representations of the complex representations. So I might be getting more of that out of regime error that you see there on the right. So with that, now that we clearly have an understanding of the uncertainty estimates that we're tasking our models to calculate for us, next I'm going to go into some simple approaches that we can use in our neural network models to actually estimate the uncertainty. So for this, I've provided a list of some of the more popular methods that we're seeing in the literature right now. And I'm going to draw your attention to 4 that I'm going to go into more in depth with. And I will also just quickly say that code for all of these is also provided in the notebooks and that GitHub link that I showed at the beginning of the talk. So the first method is parametric distributional prediction, or PDP. So the key idea for this method is to train a neural network to estimate the parameters of a probability distribution. So that's kind of what I'm trying to show in this diagram on the left. We see the input variables in X, and as we feed that into our neural network model, we're then getting the output parameters of a probability distribution itself. So for a normal distribution, say, we're estimating the mu insignia or the mean and standard deviation of that distribution. And for this method, to get uncertainties using it, what you're going to do is you're going to choose the distribution that you want, such as that normal distribution, or another popular one that has a little bit more freedom is the arc-sine distribution. And then in your neural network model, you're going to change that loss function to a negative log likelihood. And then again, replace that output layer. So instead of actually making predictions of the values themselves, you're predicting the parameters of the probability distribution. And we have, again, provided examples for this in the regression notebook. And this methodology can be used for regression tasks, but not really for classification tasks. And using this method, we can get at the aleatory uncertainty, but we can't really get at the epistemic uncertainty. So kind of just to summarize, pros of this kind of approach is that there's actually relatively minimal model changes, and it does provide the capability of capturing the Y-true spread. However, its cons are that the distribution actually must be specified a priori, and it doesn't get at that epistemic uncertainty. So the next method that I will briefly go over is the nonparametric distributional prediction, or NPDP. And the key idea here is to train your neural network to predict summary statistics. So in this case, we might want to predict a set of quantiles. So to add this to our existing neural network model, we're going to choose the number of statistical bins that we want to calculate, and then change to a custom loss function, such as the quantile loss. And then we're going to replace that outer layer with a custom layer to get at the number of bins that we are trying to actually predict. And then one last step for this is that you might need to modify the architecture in order to prevent crossover between those different bins that you're predicting. An example for this is provided in the classification notebook, and it can be used for both classification and regression tasks. So pros for this is it's relatively straightforward model changes, and it can be used for both classification and regression, and again, gets at the aleatory uncertainty. However, cons for this approach are that, again, you have to specify the number of statistics that you want a priori, and you're, again, not getting at that epistemic or out of regime uncertainty. So the next method that I'll briefly talk about is ensemble prediction. The key idea here is to train your neural network to estimate an ensemble that represents the data distribution. And to add this to your model, you're going to choose the number of ensemble members you want, and then you're going to change to a custom loss function. And one that's used quite a bit is the continuous rank probability score, which I will actually go over a little bit later in the talk. But basically, you can use anything that's going to allow you to predict and to have the model actually learn the different ensemble members so that it can optimize the ensemble members to really get at the full distribution that you're seeing in your data set. And then you're going to just replace that output layer with the custom layer, again, that is the same size as the number of ensembles that you're predicting. And again, there's an example of this in the regression notebook, and it can be used for both regression and classification tasks with some minor modifications. And again, it gets at that aleatory but not epistemic uncertainty. So pros here, without actually describing the distribution in the data at all, you can fully represent that target distribution. So it's very useful for tasks that have co-occurring target regimes. However, the con is that you do have to kind of give an idea of the number of ensembles so that you can set up your output layer, and it doesn't, again, capture that epistemic uncertainty. Which leads us to the last method that I want to briefly go over, and that's Monte Carlo dropout. So as is true with most Bayesian deep learning, this method allows you to get at that epistemic uncertainty. And the key idea here is that each neural network weight is no longer a single value, but instead is a probability distribution. So then for every prediction call, the model then randomly selects the weights and a new ensemble is drawn, which allows you to create, K number of ensembles by running the model K times. To add this to your neural network model, this is actually very simple. You simply add dropout layers, which you've probably already used in training your model so that you don't overfit your model. So it's very simple. And if you use a traditional loss function, such as the mean squared error, you're only going to get that epistemic uncertainty. However, the beauty of this approach is that it can be easily combined with a custom loss function from one of the previous approaches, and you can get at the aleatory uncertainty as well. So pros for this approach is it really doesn't require any model changes. Just make sure that you have the dropout layers and that you have them turned on when you make the inference and the predictions. And it can be used for classification and regression tasks, and it predicts that epistemic uncertainty. The con is that Monte Carlo is required at runtime, so if you have a really complex model, this actually could be insignificant, or could be a significant source of time. And also, if you use a traditional loss function, you're not going to get at the Y-true spread or that aleatory uncertainty. So now I've gone over 4 different methods to choose from that you can use to calculate uncertainty estimates. So the next step then is, how do we know if they're any good? So next I'm going to go over some different methods to evaluate our uncertainty estimates. Okay, so again, returning to that real-world example that I showed at the beginning of the talk, I'm going to use 4 different methods to calculate both the predictions and then the uncertainty estimates. So the 4 that I'm choosing to use are the probability distribution prediction using the normal distribution, which will be shown in orange, the sign arcsign distribution, which will be shown in green, ensemble prediction using the CRPS loss in purple, and then finally Monte Carlo dropout, and that'll be in pink. Now for the Monte Carlo dropout, I will say that I only use the mean squared error loss. And so that, as we know, as I just showed, does not capture the aleatory uncertainty. And for the test that I'm going to be showing, I didn't actually go and create out of distribution samples in the testing set. I'm really focused here on the aleatory uncertainty. So I'm really expecting the Monte Carlo dropout to not really perform really well, since I'm not really giving it a chance to do what it does best, which is get at that epistemic uncertainty. So I'm going to start with some graphical methods to evaluate total uncertainty. So the first will be a spread skill plot, and the idea of this is for a given predicted model spread, what is the actual model error? And this is based on a study that was by Monash et al. In 2013. And then the next will be a discard test. So the idea of this is, does the model performance improve when the most uncertain cases are removed? And this idea was used by Barnes and Barnes in 2021. And then the last graphical method that I'm going to use to evaluate the uncertainty estimates is the probability integral transform, or the PIT histogram. And this is kind of looking at, are the predicted uncertainty estimates well calibrated? And this was first introduced by Hamill back in 2001. But before I get into evaluating the uncertainty, just keep in mind that, of course, we want the predictions themselves to be as good as possible. So we need to evaluate the central value before we get into evaluating the uncertainty. And one very useful way to do this is to use an attributes diagram. And for this, what we're really looking at is for a central model prediction, what is that actual true value? So I'm going to start, and I will just say again that the code for these is in the notebooks. So I'm going to start with that attributes diagram. So let's first see how these different methods are doing in capturing that central value. So again, we're looking at, for a given prediction, what is the actual observation? And we're going to plot that relationship. So on that x-axis is the prediction, and then on the y-axis is the mean observation. And again, since this is dew point, the units that we're looking at are degrees Celsius here. Now, in reading this diagram, diagonal is ideal, right? So we want the predictions to match the observations. And if we're above that diagonal, our predictions are lower than observed. And if we're below it, the predictions are actually higher than observed. Now, as we're looking at this diagram, we can also look at two single value metrics that go along with it. The first is a Breyer skill score if you're looking at classification tasks. And if you're looking at regression tasks, the analogous concept is the mean square error skill score. So that is what I'm actually showing here in the in parentheses. And what we see here is that we see that all the models captured the central values quite well. And if we look at the SHASH, what we see is if we look at that very lower left corner, we see that perhaps it does predict too cold of those lowest temperatures. However, one of the benefits of this is we can also inlay the histograms of the frequency. So if we look at the observed frequency in that inlaid histogram in the upper left panel, we see that at those very cold temperatures, less than say -80, we see that there's not really very many observations. So that could perhaps explain the model's not doing quite as well at predicting those because maybe there just wasn't quite enough training data for it to fully learn that relationship. Okay, so that is the attributes diagram. So now that we've evaluated our central predictions and we see that all four of the different methods we're looking at are doing a pretty good job at getting the central values. Next, we want to see, okay, how different are we seeing the uncertainty estimates between these different approaches? And the first way that we can get at this is a spread skill plot, which is shown here. So for this, again, the key question that we're getting at is for a given predicted model spread, what is that actual model error? So here on the x-axis is the spread or the standard deviation, and then on the y-axis is the scale or the root mean squared error. So again, we want it to be a one-to-one relationship, so lie on that one-to-line diagonal line. Above that diagonal line, our uncertainty estimate is too low, so the model is overconfident. And if we're below it, the uncertainty estimate is too high, so it's overdispersive, or basically the model is underconfident. And just like in the attributes diagram, there's a couple single value metrics that we can also get using this diagram. The first is the spread skill ratio, and that's basically the spread divided by the skill or the root mean squared error average over the entire data set, where the ideal value would then be 1. And the second is the spread skill reliability, or the weighted distance between the spread skill line and the one-to-one line. And again, that ideal value is 1. So now if we look at how our different models are doing, what we see is that the Monte Carlo dropout in pink is hovering over there well above that one-to-one line in that lower left corner. So that model is quite overconfident. If we look at the other three models, what we're seeing is that both the PDP and ensemble prediction methods are performing pretty well for those small uncertainties. However, once we get above 10 degrees Celsius, we see that they become underconfident. But again, we can also, for this, inlay a spread frequency diagram. And as we see here, there's very few samples for that. So in general, I think we can say that for most of our predictions, our models are actually doing a pretty good job at getting at the uncertainty estimates. So the next test we can do is the discard test. So this is getting at, does the model performance improve when the most uncertain cases are actually removed? So here, as you know, as implied by that statement, we're going to discard the samples with the highest percentage of uncertainty, and then we're going to calculate the model error when the remaining samples. So in reading this, the bars for each model should decrease from left to right. So as we remove more and more, we hope that our model performance improves. And again, from this, we can get a couple of single value metrics. The first is the monotonicity fraction. So how often does the error decrease when we discard more and more samples? And again, we want an ideal value of 1. So we want to continue to see improvement as we remove more and more of the uncertain cases. And then the second single value metric would be the discard improvement. So how much does the error decrease on average? So higher values are better. We really want the model to start doing really well as we really narrow down on the most certain cases that it's predicting. So now if we go ahead and look at how our model is doing for our real world sample task, what we see is that all the models do have a decrease, a monotonically decreasing or improvement in the root mean squared error as we continue to remove the uncertain cases. However, the improvement is much greater for the PDP and ensemble approaches than for the Monte Carlo dropout. So then the last graphical method that I want to go over is the probability integral transform, or the PIT histogram. So the key question here that we're trying to get at is, are the predicted uncertainty estimates well calibrated? So just to provide some background on the PIT diagram itself, the PIT is the cumulative distribution function, or CDF, of the predicted distribution, and this is then evaluated at the observed value. So this can be interpreted as the quantile of the predicted distribution at which the observed value occurs. So what I've shown here is kind of an example. So if we look at the blue dots are then the data that we're trying to estimate, and the gray is the 95% confidence interval where that median of the model prediction is shown in the orange line. So to calculate a single value of PIT, what we're going to do is we're going to evaluate, say, at x equals 7. So we're going to pull out that slice right where x equals 7. And at that point, we're going to actually calculate the PDF, and we can also get at the CDF, for that cumulative distribution function. So we go ahead and plot that for our model, and then we can compare that to what the true mean actually is, and where the CDF is evaluated at that true mean. So here we see that the true value there, or that y value, is -10. That evaluates to a CDF value of 0.63. So that's our PIT value at that 0.63. So we can do that across the entire data set, and then we can make histograms of that, and that is what our PIT histogram is showing us. So that's what's shown here. And then to read this diagram, as we divide it into usually tenths, and you want an equal distribution of your uncertainty to lie in each of the different bins. So we really want this flat histogram, and that would indicate that our uncertainty is perfectly calibrated. If we see a hump in the middle, our model is underconfident, so our uncertainty is overspread again. And if it's higher at the end, it's the converse. So the model is overconfident and our uncertainty is underspread. So as we see here, which we kind of are already getting a picture of from our previous two graphical ways that we were looking at it, the Monte Carlo dropout method is overconfident. So it's actually underestimating the uncertainty spread. However, all the other models are also doing okay. So as with the previous metrics, is another single value metric that we can derive from here if we just kind of want to quantify this diagram into a single number, and that's the PIT D value, and that's the PIT calibration deviation score. And it's the mean difference between the actual bin frequency and the expected bin frequency for a uniform histogram. And the ideal value should then be 0. So if we can go ahead and look at those scores, as I've shown in the parentheses of the legend, we do indeed see that that Monte Carlo dropout has a much higher score. So it's performing much worse in this PIT test than the other 3 models, which all have very similar scores. Okay, so those were the graphical ones. And then as I've already given definitions for, there's a bunch of single score metrics, and these can be very useful in comparing your uncertainty estimates. So we saw, the prior skill score and mean square error skill score from the attributes diagram. From the spread skill plot, we saw the spread skill ratio and reliability. Discard test, we saw monotonicity fraction and discard improvement. And then from the PIT histogram, we saw that PIT D value, or the calibration deviation score. There's two more scores that I want to go over that can be very useful as well. And as the first is the continuous rank probability score that I've already kind of alluded to, and that's getting at how well the predicted distribution captures the true spread. And then the second is the ignorance score, or how much the predicted distribution is concentrated in the correct areas. So the CRPS, or continuous rank probability score, this is really a comparison between deterministic models and probabilistic models that was actually used several years ago for just ensemble predictions in general. And in fact, this community might actually be quite familiar with this already, but in case you're not, I'll briefly go over it. And it's really a probabilistic adaptation of the mean squared error. So the equation is shown in the equation here on the left. And so you're really looking at the predicted cumulative distribution function, or the predicted CDF again. And from that, you're subtracting this Heaviside step function. So you're going to give it a 1 if you're greater than the true value, or a 0 otherwise. So this metric varies from 0 to infinity, with the optimal value being 0. So you don't want any difference between the model and the observed value. So this is kind of shown graphically in the figure on the right. So we see for a deterministic model, we see the straight up line at the actual value where y is. So for the truth, we see, it's kind of in the middle of that graph there in that blue line. And then perhaps for our deterministic model, it might be, say, shifted slightly towards the left. And we see that the CRPS score is then that difference in the area between the deterministic model and the truth value. So it's kind of that green shaded area. And then for a probabilistic model, if we look at the CDF at the value, we see that it's now a distribution. And again, we can see that the area difference between the truth and the CDF is what's going to give us our CRPS score. So just kind of one more example of this. If we look at a distribution that might, say, have kind of like a point distribution, we might have points that are increasing and then some points that are lying along that 0 line. And if we're trying to predict that with a model, if we use just a simple, absolute error model, we might get something like the green line, where it's trying to average out that difference between the points that are increasing and the points that are staying at that 0 line. However, if we use an ensemble approach, we could get ensemble members that do a pretty good job at capturing those two different target regimes that capture both the increase in the data and then are also overlying on that 0 line for those data points that are just remaining at 0. So if we pull out that slice at, say, 1.5 and calculate the cumulative distribution function at that value, that's what's shown in the right-hand diagram. So the truth is in that blue line, and then the mean absolute error model is in green. So we see at that target value, it switches from 0 probability up to 100% probability. And that creates quite a large difference between our actual CDF function, which is shown in that green area there. So we have a pretty high CRPS score. In contrast, our ensemble members, if we go ahead and plot the CRPS or the CDF at that 1.5 value, we see that the differences are shown there in that purple shading. They're actually quite small, and our CRPS score is much lower, much closer to 0, indicating that, yes, the ensemble approach is doing a much better job at getting at the distribution that we're actually seeing in the data. So just to reiterate, advantages of this are that we can now consider the fully predictive CDF, and we don't have to just look at, this mean or standard deviation or any certain quantiles or everything. We can actually just have the model get at that CDF by itself. And it can be used as a loss function, as I have done and, provided examples for as I work through this talk. So it actually creates ensembles of predictions, and if you use it in that loss function, it optimizes those ensemble members to really represent the data distribution itself. And I've also provided some other works that have used the CRPS that can also provide excellent derivations if you'd like to do more research on the CRPS score. So the last score that I'll get at is the ignorance score, and I'll just briefly go over this. This is just basically a measurement of how much the probabilistic forecast is concentrated in the correct area. So the equation is shown there. It's pretty simple. You just take the PDF and then you take the log base 2 of that. And this, again, varies from 0 to infinity, with the ideal value being 0. and it really does reward correct high confidence predictions. So it wants to get as narrow predictions as possible as long as they contain the observed value. So finally, I'll end with going back to our real world example and show you all the related scores for each of the 4 different uncertainty estimate approaches that we used. So just highlighting what we can see now from the scores themselves. If we look at the root mean squared error and the mean squared error skill score, our mean predictions from the 4 different models have nearly equal skill. So they're all doing a good job at getting at those central prediction values. However, we start to see differences when we look at the uncertainty estimates. The Monte Carlo dropout produces the worst uncertainty estimates, as we can see by the worst scores for the other metrics that are getting at those uncertainty estimates. And then if we look at the PDP and ensemble approaches, they have nearly equal skill. And I guess if you look at them more closely, you could perhaps say that the PDP is perhaps not quite as good as the CRPS. So if I had to pick maybe one model, I might say that the ensemble prediction with the CRPS loss function might be edging it out slightly, but we see that their performances are actually pretty similar. So with that, I will just end with some ending remarks. So what I've gone over today are some simple methods that can be used to go ahead and derive those uncertainty estimates from neural network models. And just as a note, different methods can yield higher performances for different tasks. So it's kind of good to have in your wheelhouse maybe some of these different approaches, as you do have different data distributions and different tasks that might take advantage of some of the pros and cons of some of the different approaches. There are also some simple methods that we can use to evaluate our uncertainty estimates. And as I showed, the graphical methods are kind of nice. They can be used to provide quick insights into the model uncertainty performance. But if we really want to compare like between different models, single value scores could be very nice. And they can kind of allow for easy, quick comparisons on tables where we can just quickly glance down and see, okay, this approach is working better for this task. And just as a caution, the evaluation methods that I've gone over here get at the total uncertainty. They really don't distinguish the components. So as we saw at the beginning of the talk, the contribution of uncertainty components really does depend on your data set choices. And for the machine learning definitions, at least, if you add different features, you're kind of shifting between these different components. So it's kind of important to keep that in mind. And this out of distribution error is a key component of the ML epistemic uncertainty, but you really only can see it if you have a test data set that includes samples that are really different from the training data. And I haven't done that at all with the work that I'm showing it. So for what I've gone over today, I'm really only getting at that aleatory uncertainty. And then as we saw today, we saw that the Monte Carlo dropout method perhaps didn't perform very well, but that's not really surprising because we didn't allow it to be tested over epistemic uncertainty, which is leads me to my last slide of comments, which is that I think that the challenge now is, now that we have these methods that can do them, we really need to be able to use them and interpret what they're saying and be able to then share them with the community in a responsible manner. And I think there's still a lot of questions that we're still trying to iron out, or at least I'm still trying to learn, which is, how do we ensure that we can get these out of distribution samples to provide a representative epistemic uncertainty, especially if for those out of regime answers, we may not know what the truth actually is. So how big should those uncertainties actually be? I think this is kind of still an open question that a lot of people are still looking into. And then finally, once we have these estimates, we understand them and we can interpret them, how are we going to actually share them, particularly for images? As I provided for the task here, it was pretty straightforward because it was vertical profiles, but I think as we move to more tasks such as even climate modeling, as we saw, where we're looking at maps, what is the best way then that we're going to actually convey them, the uncertainty estimates that we're actually getting in a helpful manner as we move forward? And with that, I will just end with my references, and then I will say thank you and take any questions.